Hi there. The original title was Performance Improvements in 3, 14, and 15, but I've changed the scope a little bit, so I've just given it a slightly more general title. So the first thing I want to do is I say there's no silver bullet. We've had lots of talks about JITs yesterday, and lots of talks saying the JITs weren't silver bullets, and this is kind of the reason why. Kenjin had a similar slide to this. This is just the pie chart version. I guess I kind of like more management levels, so I have to use pie charts rather than like tables. And you can see there's like the purple bit on the top left is the interpreter. To the top right is the garbage collector. On the right, the JIT compiler. And the interpreter does take a big chunk of the time, but some of that's moving onto the JIT, and as we make the JIT more general and able to interpret more code or with lower thresholds, that number will swing from the interpreter to the JIT. So the two are still very important parts, but there's also lots of stuff to do with memory allocation and the cycle garbage collection. There's still lots of C code in the interpreter, in the Python runtime, and so lots of lookup and dynamic code in those, when that's the bit, and then there's just a whole bunch of other bits and pieces. So there's no kind of like one thing we need to speed up. We kind of need a fairly general approach. So first of all is the interpreter, but that's already been done. Kenjin did an excellent talk on that, and realistically the interpreter is getting to quite mature state. The tail calling interpreter in 3.14 is probably like the only thing that's likely to be happening to the interpreter in 3.14, 15. I mean, it's still lots of like bugs to fix it around the compilers and so on, but it's probably in terms of like interesting sort of technology, that's kind of it. So if you weren't here for the previous talk, you'll have to go and watch it online. So what about the JIT compiler? Well, Diego covered that yesterday, so if you didn't see that yesterday, you can go watch that online. If you want to see it like sooner than that, then Brant Bucher did some really good talks on the JIT compiler at PyCon this year and last year, so I'm kind of running out of things to talk about here, but there are a few bits in the JIT. So 3.15, we expect further improvements. So again, if you saw any of the JIT compiler talks yesterday, one of the things we do is like redundancy elimination, so repeated checks. So if we check the type of an object and then check the type of the object again, we can remove the second type. We'll add more of those in 3.15. We can add unboxing ints and floats. I've got a question mark after this because I'm not sure when we'll be adding that. It may be 3.15, might be 3.16. That's kind of important because that saves a lot of memory traffic as we take an integer or a floating point number, and we can move it from one place to another without having to do additional memory transfers or allocations. And the last one is register allocation. Register allocation is an important thing in compilers. In the previous talk, we were seeing how it's an issue for the C compiler, but in our JIT, we also want to do register allocation. We use a technique called top-of-stack caching. It's called top-of-stack caching because the Python VM is a stack machine, and that means, but the top of that stack is in memory, but it's much more efficient if we can keep the top in registers. And this top-of-stack caching is effectively a simple form of register allocation for stack machines. So, as an example, we have C equals A plus B. The instructions are on the left are load fast, binary op, store fast. That just, load fast takes the named local variable and puts it onto the top of the stack. Binary op takes the two items off the top of the stack, adds them together. In this case, I should have put binary op, I should have put plus there, but it doesn't really matter. And the store fast takes the value off the top of the stack and puts it back into the local variable. Now, the current implementation, all the local variables and the stack are in memory. So this is quite inefficient moving a local variable to the stack because we have to read it out of the local variable and then we write it back to memory and the stack. So you can see at the bottom that's 5 reads and 4 writes. Generally with modern CPUs, ALU operations cost a cycle or even less, which sounds a bit odd, but they can do several at once. Register-to-register moves are often free, cycle at worst, but memory moves can be anywhere between 3 and 100 cycles, so we definitely want to be avoiding the memory moves. So if we put the top of the stack in the registers, we just call it register 0, register 1 here, and they're on blue on the right, we can see we're doing essentially the same set of operations. We're moving from memory from the locals to the stack, but by having the stack in the registers, we're moving from memory to registers, registers to registers, and then register back to memory. And that's much fewer writes. and much fewer reads as well. So top-of-stack caching, JIT compiler, integer tagging. I thought I'd have a fun little demo. Now, the picture here is from Antonio Cooney from 2017, I think, where he uses a contrived demo to demonstrate how PyPy is 400 times faster than CPython. So what I'm going to do is I'm going to use an even more contrived demo to show how much faster a hypothetical CPython 3.15.16 will be than CPython 3.10. So first of all, we'll just have a look at our silly little program. It basically just adds a bunch of numbers up. Well, it has one. It doesn't really do anything useful at all. But it has a little branch in there that should never be hit, and we put a breakpoint in there. And the breakpoint is the important part of this contrived demo. So what we're going to do is we're going to run this with PDB into 3.10. And I can put the breakpoint in. Which line do we want? 6. And then we'll just let it run. So in 3.10, PDB used sys.sesstrace, and that adds quite a lot of overhead. As you can see, this is really slow. So chat amongst yourselves for a little bit. It's not that slow. It should take about 20 seconds. And I don't know how long 20 seconds is. Soon. Anyone got a joke they want to tell? There we go. 28 seconds. Excellent. My contrived demo is slower on that, so it'll look better. So, okay, no, that was 3.10. Now we'll do the same with this one I've locally compiled. So what was the 6, wasn't it? And it takes 64 milliseconds. So I don't know how much is that. Is that 400 times faster? No, probably not, but it's getting close. So there we go. Right, just for to tell you what's going on there. Of that roughly 400 times speed up, 80 of that is because of the better PDB we have. So, you know, a bit of a cheat. But yeah, PDB is something like 80 times faster in most recent versions of CPython. I'm not sure if that's 3.13 or 3.14. Tiangao implemented that using the new sys.monitoring. So yeah, that's 80-fold. The other 5 is from the unboxed integers and the top-of-stack caching in the JIT. So you know, it's a significant speed up on the others on this little toy program. Anyway, so back to the slideshow. So when you write a Python program, you're like create an object, access bits of an object, attributes of an object, create other objects, look at objects. Everything's sort of objects. So the memory layer of Python objects is kind of important for performance. JIT compilers are all very cool, and all those sort of operations I was talking about, we can speed those up. But they still, all these objects like take memory, and the more memory you use, the slower stuff gets because you get worse cache effects. Things just slow down. So I'm going to give another little contrived example. This is slightly less contrived. This is a very simple object. It's got 4 attributes. So here's just an example. Its dictionary is just A1, B2, C3, D4. Yeah, and it's got 4 attributes. So if we go back to prehistory, I can't remember anyone. Who actually used Python 2 here? Go on, hands up. Oh, that's a fair number of people, so you remember these days. So this is anything prior 3.3, so no one used 3.1 or 3.2 anyway, so this would be 2.7 effectively. So the thing I want you to see here is that object, there's a lot of stuff going on here. Very briefly, there's a lot of headers to do with the garbage collection, there's a reference counting, there's a class pointer and everything. Every object has a dictionary, and the dictionary itself needs a table or its data in. There's a lot of wasted space everywhere. So there's a couple of things here. One is you use a lot of memory for something that's effectively 4 machine words of data, and we're using 44. And there's a lot of memory accesses to access the attribute c.a. So to access c.a next 5 memory accesses, and that's a theoretical minimum, assuming you have like an advanced specializing interpreter or a JIT that's already got information about this object. In practice, without all the modern optimizations we're doing, would have taken way more than 5 memory accesses. But But this is like a lower limit of this sort of design. So obviously that was pretty efficient. So yeah, there's a bit of, you can see the hashes and the keys are redundant because the expectation that all classes would sort of share the same one. So in Python 3.3, we got rid of that, and those keys are now shared between all the classes, well, were shared. Well, sort of still are in some circumstances, but you'll see how this changes. So this is smaller, but you notice the actual memory access now is even worse because these keys are in a different location to the values, so you have to do an additional memory access. So while this saved memory, you're actually making things potentially even slower. You can see there's still some space in the table. So in 3.6, we did what's called the compact dictionaries. And the way they work is that the keys look up at, instead of the keys mapping to the value, they map to an index in the table, and then we can have a compact table. Again, this saves a little bit more memory, but we're still looking very slow. We're still doing 6 memory accesses. In 3.6, we compressed the headers a bit. You can see there's a bit of redundant sort of alignment issues, wasted space there. We shrunk the GC header a little bit. And we're now down to like half the size we started with. So the memory management stuff is improving, but again, we're still 6 memory accesses. This is still pretty slow. But that entire dictionary is actually redundant because now all it has is, it has no additional information that isn't present in all those other places. It has the keys and the values. Well, the values are in that table. The keys are accessed from the class, can be accessed from the shared on the class. So we can just get rid of this. And this is in 3.11. And this is a nice, we're now starting to get a lot quicker here. Again, we saved quite a lot more memory, which is nice. But notice the memory accesses have dropped from 6 to 3. So we've effectively halved our amount of memory accesses to access attributes. And attribute access is a pretty important thing in most Python programs. In 3.12, we shrunk it a tiny bit. Again, 3 memory accesses. And in 3.13, we've managed to what's called, we've inlined all the values into the object. So this is nice for a couple of things. It's a single memory allocation, which is faster. And we're down to 2 memory accesses for the attributes. I think, realistically, 2 is the lower limit. Obviously, theoretically, you only need the 1 to actually just read the value. But because Python is so dynamic, I don't think there's any way to not have an additional read to actually check the state of things, that things are as you expect. And you'll notice the memory size has gone up slightly from 3.12 to 3.13. So again, we're trading off a little bit of memory for speed. But given how much money we've saved, well, money if you're paying for your memory, I guess, how much memory we've saved, I think that's worthwhile. So CPython is reference counted. And we do a lot of reference count operations. I think the order of reference count operations is like in the same sort of order of bytecode instructions we do. It's a huge number. And those can be relatively expensive. Each one is obviously one of these little tiny cheap, fairly cheap operations. The sheer number of them is what gets to us. So there's 2 ways we can kind of make things faster with reference counting. One is just to do fewer of it, and that's sometimes just things like how we organize the C code, whether we pass a reference from a caller to a callee, or whether we lend it. If we lend it, it has to be incremented and decremented afterwards. If we give it, then there's no requirement for that. Little things like that. But one of the quite significant things we made change in 3.14 is this deferred reference counting. So the way this works is that normal reference counting, the reference count is on the object. So we have a pointer to an object. I've just put the zeros at the end because all pointers are aligned. You'll see why that's in a second. And to do the reference count, we have to do 3 operations. We have to move the reference count from memory into a register, increment the value in the register, and then write it back again. And modern hardware likes to do stuff in parallel, and these are what's called dependent operations, which means you have to do them sequentially. So that tends to slow things down. What we could do is have a reference count stored on the pointer. Now, this is obviously you can't do that in general because you wouldn't be able to find these reference counts, but we can do it in special cases. And the advantage where we can do this is because CPython is a stack machine. Stack machines have like the first in, last out property. if you know you have a reference to an object on the stack and you add another reference on the stack, that second one will always be outlived by the first one. So you can just put one of these little pointers in the references in the pointer. You still need to record it somewhere for the garbage collector to work properly, but it's much, much cheaper doing this way because it just goes in the pointer and not in the object itself. So we've dropped from three things to one. Now, going back, I said earlier, to boxed integers. Now, notice again, we've got these last two values, and we've already tagged one for these reference counts, so we're starting to sort of like abuse these pointers a bit to be not quite pointers with a bit of additional information. And one thing we can do is tagged integers. Now, tagged integers are a very old technique. I think it was used like early Smalltalk and some of the early sort of dynamic language virtual machines back in the 1980s. And this is a fairly simple thing. Again, we put a tag at the low bit of what was a pointer, and is no longer a pointer at all. It now just includes the value of the integer. And then we just don't need the integer at all. And we just replace the whole thing on the left with just this value. And that's what I was doing in that earlier demo. That had tagged integers, and that meant that basically all those integer operations, and that's why it was so contrived with the +1, because I didn't want it overflowing what could hold here and slowing down. So as I say, super contrived example. But in practice, most values will fit in there. I mean, 2 to the 61 would do plus or minus 2 to 61, which is what you can fit if you've got two tag bits and a 64-bit integer. That's an enormous number. I mean, 2 to the 60 is what? Trillion. So I mean, like, any practical purposes of like integers, apart from like things like cryptography or something, where they use like integers in the sort of mathematical sense rather than just the practical, like a number, will fit in this value. So essentially that means we don't have to box or unbox all the integers. And integer ubiquitous in all programs. So like if you have like mathsy programs, sure, you have loads of floating points. But like normal programs that are just web servers or so on, like lists have lengths in them. It's an integer. Strings have lengths, an integer. All the Unicode characters are integers. Integers are ubiquitous. So this is a potentially quite a powerful optimization. It might take a while. That's why it says maybe 315, because it's one of those things. It's quite an intrusive change, so it's one of those things that may well take time. How are we doing for time? Whoops. Yeah, I think we've got enough time. So garbage collection. So Python is reference counted. CPython is reference counted. Sorry, I'm just all the PyPy and growl pile people cringing when I said that. So CPython is reference counted. And the idea being, obviously, each object has a reference count on it, and when it drops to 0, it's freed. But there's a problem with cycles. So if you have a cycle of objects like this in this picture, each of these objects has a reference count of 1. None of them are reachable. It's all garbage, and you'll never collect them. So we do have what's called a backup cycle collector, and actually takes up a significant amount of the runtime. I think in the original, it was like 9% or 12%, something. Anyway, so there's a couple of improvements. One is actually happening in 3.14, and one maybe for 3.15. So the first one is incremental garbage collection. So incremental garbage collection is what it says. It just does it incrementally. So instead of collecting the whole heap at once, it collects like an increment at a time. So the 3.13, so any garbage collector in any Python you're currently using, is what's called a generational collector. So it'll try and collect a small portion of the heap repeatedly, and then eventually it'll have to collect the whole heap. And that can result in long pauses. And because of we can't do it too infrequently, otherwise too much memory just gets piled up that needs garbage collecting. So with an incremental collector, we have a means of just doing part of the heap and then another part and so on. And once we've worked our way through the whole heap, we'll have collected all the garbage. We'll have collected all the garbage that was garbage at the beginning of that sort of pass-through. And this is a bit faster because we can, change the thresholds a little bit because we're constantly doing it, so we're less laggy in sense of sometimes. But mainly it's lower pauses, so you shouldn't get like long pauses while we collect the entire heap. So that's a slight improvement. In 3.15, or possibly later, hoping to do what's called candidate root garbage collection. And I'm using this as an example, I think, as one of these nice optimizations that becomes feasible because of other optimizations. So a root of an unreachable cycle is the last object in that cycle was reachable from outside of the cycle. So on the left, we have a reachable cycle. There's an incoming reference to the blue object. And then when that reference is removed, we then have a cycle. And that blue object was the last object that had a reference to it. Now, this is interesting because you notice that last reference, let me go back. That last object has a reference count reduction from 2 to 1. So any object where the reference count is reduced to non-zero could be a candidate root for a cycle. And this is interesting because it scales well, because it doesn't need to scan the whole heap. It can just scan, like, it just looks at these candidate roots. But unfortunately, if you have lots of reference count operations, we end up tending to have more candidate roots than we have objects, really. I mean, like, everything ends up being a candidate root, so it's pretty useless. But other optimizations we're doing in the VM that reduce the number of reference counts, like that deferred reference count thing I was explaining earlier, and other improvements we can make, mean that this becomes a more viable operation. So this is one of these things where, although we have all these many different aspects of the VM that we want to improve, you know, memory management, the cycle GC, the interpreter, the JIT, and so on, there's a number of cases where we have optimizations that in themselves aren't that valuable, but they enable other optimizations. So it's always this constant sort of cycle of sort of improving one thing allows us to improve something else, and so on. And this one is particularly requires fewer reference count operations to be efficient. But if we are keeping making iterative improvements, we need to keep making iterative improvements. So it means someone has to pay for this. So if your company spends a lot of money running Python and would benefit from the continued improvements, come and talk to me, because yeah, this needs funding. And yeah, it would be nice. And the more people working on it, the faster it goes, the better things get. I mean, collectively, I don't have any idea how much money is spent running Python globally, but I suspect it's in the billions. And a small fraction of that would prove Python a lot. Okay, and I think that's it.
All right, thank you so much. As we're really good with time, do we have some time for a question, if anyone has one?
Hi, I just wanted to say I was really inspired about these slides about the memory organization of objects and so on. Do you know if there are any tools to inspect like the state of Python at runtime and see here is what's occupied by this object and like this is how much memory are my objects taking and so on?
I don't know if there is, although admittedly I was thinking I should write one while I was doing these slides.
Please do.
I'm thinking it's one of those, like, I'm thinking maybe we could implement it in Python, just dump out like a tuple of like the layout and then have other tools to present that nicely.
Thank you.
Hi, thanks for that talk. I have a question regarding the in-pointer reference counting. I guess it's only valid for like a low number of reference counts.
No, I mean, in theory, you could have like 100 objects, all of which refer to each other, and everything would have a reference count of 100, and the last object's 101, and then it goes reduced to 100. So it's any number. Unfortunately, yeah, because it would be nice if you would, because that would be a nice filter to sort of make this more efficient, but it could be any number.
So I'm not talking about this slide, right? I'm talking about the one where, that one, yeah.
Yeah, you get one in there. So each pointer is a reference to an object.
Yeah.
So basically, by storing the one in there, you've reduced the reference count in the object is one less. And that can only ever be one.
Right.
Because it's just one reference.
Okay, I see. Thanks.
I have a question about this tagged integers. If I use this get ref count, does it change anything if you use tagged integers, or there's no changes there?
So what number you'd get there? I don't know, I'd have to go and look. Well, okay, so the tagged integers is only really, and this example is like only in the interpreter. So as soon as you're passing out to like an API function, we create an object and you'll get whatever object number that has.
Okay.
Ultimately, though, as we broaden the tagged integer across the whole thing, then I guess we just make up a number.
Okay, because I show other people just
one,
get ref count,
probably.
and if there's nothing coming back, that would be an exception.
yeah.
I would need to explain this one. Okay, thanks.
All right.
All right, since we have some more time, does anyone have any more questions? If you think of them, you can still come to the mic and ask them. If your curiosity is satisfied, I do have one announcement before you all go. I was asked to announce that the PyLadies lunch will be happening at 1 p.m. sharp in the VIP lunchroom. But other than that, please thank you again for your presentation.